idea of kind of deconstructing the database has been a project that's been happening maybe over the last 10 years or so. The Hadoop revolution was in part about that. And this talk is this isn't about any particular database system. I will be talking about Calcite from time to time. But really it's a talk about the laws of physics that determine what makes a good data system and some of the tricks that have been used really since the very first days of databases, and how we can apply those to the next generation of systems. And if you're not writing a database, which I expect most of you are not writing a database, it's useful to know these things simply just to evaluate whether this is a sound data architecture. I hope that it's useful for people that are doing data engineering and not necessarily building their own database management systems. So quick intro to me. I do a lot of open source work with the Apache Software Foundation, in part because that's where a lot of interesting big data stuff is happening. I've been doing open source for a very long time, going back to, I built the Mondrian OLAP engine, which is the first open source OLAP engine back in 2001. Contributed to a variety of projects, but the main one that I'm involved with is Apache Calcite. More about that later. I was at Hortonworks until recently, and a month ago I joined Looker. So not much of this talk is going to be about Looker because I'm still learning about the company, but just a couple of things I wanted to say about it. First of all is everyone seems to love Looker. The reason I joined Looker was because I met various people that were customers of the company and they loved it. And the employees, the work environment is extremely respectful, which is important to me. And everyone is, functioning as a team. What Looker is, the quick description of it is a business intelligence tool. But what they're trying to do is to create a data culture in a company, which means making it easy for the business users to get hold of the data that they want without writing SQL or without bothering IT. But the way you achieve that is basically to provide this data model. And they have a language called LookML, which is a human readable and human writable. It's code. You write your business model in code. And then deploy that, and everyone in the company is basically seeing the same definition of all of the measures and dimensions that they're using. So, and the fact that it's code is, I've worked in BI a long time, the fact that it's code as opposed to a blob of data in a repository is a very big deal, because it means you can put it in Git, you can diff it, you can push out patches, you can do all the things you do with source code. So bringing some of that software engineering approach to business intelligence, I think, is huge. So that's why I joined Looker. You can surmise some of the ideas that I'm doing in this talk I am hoping to bring into Looker over the next few months. Okay, so to kind of motivate this, here's a so-called simple query. There's no database management system involved. And the reason is because I'm kind of thinking about the laws of physics here. Imagine if you have the 2010 US Census and 100 million household records. Each record is a kilobyte, so you've got 100 gigabytes of data. And you basically want to sum up that data. And the goal is to sum up all the data in 5 seconds. The data is stored on 4 disks, and the disks have SATA 3 throughput. The short answer is it's impossible to achieve the goal. The reason is because the disks, 100 gigabytes of data, 1 gigabyte per second, it's going to take 100 seconds of disk activity to pull the data off those disks. And yet we all query data systems that are much bigger than that on a daily basis. So, how do they do it? What is the trick? So there's a variety of solutions, and all of these all of these solutions are implemented to some degree in your favorite database management system. The simple solution is a sequential scan, and it takes obviously 100 seconds. If you parallelize the query, if you spread the data over 40 disks, then you still have to kind of coordinate the data and bring it back again. The query takes maybe 10 seconds because you've basically just got more I/O capacity. So this is the, that's the fast in my talk title. Caching the data, if you execute the query once and you cache the query result, or you cache all of the data in memory, if you happen to have 100 gigabytes of memory, you cache the results, and then you can answer the question much more quickly. But the absolute fastest way that you can compute the answer to this is to materialize it. In other words, cheat, pre-compute the result, store the result, and when someone asks that question, how many households are there in the US, you can basically, in 1 millisecond, you can basically answer that question. So, and that is the reality, that's the dirty truth, that all database management systems basically cheat. They don't answer the question you ask, they answer some similar question they've pre-computed. So I'm going to be, I use the word materialized there, I'm going to be talking a lot about materialized views or materialized queries. So don't be put off by that terminology, but as I'll explain, this materialized queries is a pattern which has existed a very long time in database management systems, way before the Oracle got the create materialized view command in probably probably 2003. Even better, sometimes you can't anticipate all of the questions that people might ask. The very best solution is to materialize, cache the results, and adapt. So if people start asking questions they've never asked before, start building new materializations to answer the question that they may ask in 10 minutes' time. So yeah, lazy beats smart and fast. Lazy meaning pre-compute the answers in advance so you just know the answer. So yeah, here are some of the questions I'm going to answer in this talk. How do you tune a data system, or how should the data system tune itself? Because you just don't, the data system on the day that you load the first data set is not going to be perfect because it doesn't know what the query load is going to be and so forth. How did we implement this in Apache Calcite? I'll explain a little bit about what Apache Calcite is and the features that you would use if you're building a database management system. What are some of the techniques you can use to organize data, and how to make the system self-organizing? So how can we bring in techniques kind of like the term self-driving database has been used. This idea of systems that learn and adapt automatically. We're going to be using a lot of, I think in terms of relational algebra. I think I dream in relational algebra. Relational algebra is what is underneath every SQL system you use, and probably a lot of the NoSQL systems as well. It's based on set theory and a small number of basic operators like project and filter, filters like the where clause, aggregators like the group by clause in a SQL statement. And it turns out using 8 or 10 of these core operators, you can represent a kind of data flow graph, which is logically the question that you're asking for. And building relational algebra is complicated because you need to build a query optimizer and things like statistics in order to execute a query based on relational algebra. That's the kind of bad news. But the good news is that once you've built a query optimizer and you've built relational algebra, you can kind of start doing a lot of really exciting things, like what the database folks call data independence, which is now your application is no longer dependent on the way that your data is physically stored on disk. So you could, for example, load your data so it's scattered randomly all throughout your disks, and then you notice you're doing a lot of joins on product ID, so you could reorganize your data so it's partitioned on product ID. So product-based joins are now going to run really fast. If you've built your data using SQL, or in fact, anything with a query optimizer, you can reorganize your data and your application doesn't have to know about it at all. If you haven't done that and you've organized your data into files, then you're going to have to completely rewrite your application if you reorganize the data like that. And so partitioning is just one of 100 different techniques you can use to reorganize your data to make the queries run faster. And also, I'm not really going to talk about query optimization, but a query optimizer can achieve stunning 1,000-fold improvements in the performance of queries. So Calcite it's an Apache top-level project. Not many people have heard of it. Actually, who's heard of Apache Calcite before? Okay, so about a third of the room. Well, that's good. That's good because it's not an end-user tool at all. It probably only has 100 customers in the whole world. People who are writing database management systems are the people that want to use Calcite. So if you're using Hive or Flink or MapD or Apache Beam SQL or Phoenix, then you're using Calcite under the covers. Anyway, it makes a lot of good things possible. We use the Apache community development model, which means we're not dominated by any one vendor. We have people from competing companies all working together under the Apache process, and they all basically put on their Apache hat, which means they are working for the good of the project and leaving their particular employer's interests at the door. And the result is we've created this really useful thing that keeps on getting better. And if you want to get involved, that doesn't mean writing code. If you just want to talk to us, ask questions, then join the dev list, the email list, and we'd be happy to help. So there's lots of ways of organizing data. There's lots of dimensions you can use to organize data. Data format is just one of them, right? Whether you store your data in awk or Parquet. If you just store the data row-oriented or column-oriented. But there's a class of organizations of data which I call logical organizations, which is if you know that the data is, if you know that data from 2016 is over there and 2017 is over there, those kinds of organizations of the data enable some kind of massive performance improvements because the system actually knows something kind of about the semantics of the data. And it can turn a query on 1 billion rows to what is really a query on 1,000 rows. In other words, it allows the optimizers to rewrite the question in terms of, it makes it into a simpler question. So a lot of the stuff I'm going to be talking about I'd call logical optimizations or logical reorganizations of the data. Lossy copies of the data is actually one that's really interesting. I was talking to someone today about Vertica, which is a kind of the first mainstream column-oriented database, came out in the early 2000s. And when you load a table in Vertica, it will create, you might have columns, A, B, C, X, Y, Z. It will create one projection of the data on maybe columns A, B, Z, and another projection on columns B and C. And it will just choose which of the projections most closely answers your query. Those kind of things where it's producing multiple copies of the data in different sort orders is a very powerful thing. So the first kind of materialized view, the one that everyone knows, is the B-tree index. One of the things I learned when I joined, years ago I worked for the kernel development team in Oracle. And I was surprised to learn that an index in Oracle is just a table. It doesn't appear in the catalog as a table, but it's structured just like a table. And in fact, so when I create an index, I've got an employee table with employee number and name and department number. If I create an index on department number and name, then it creates a table with department number, name, and row ID. And that table is physically sorted on department number. I mean, it creates a B-tree structure above it, but the actual records in it are sorted on department number. So it kind of has the same data as the table. And if I want to look up all employees in department 20, it's kind of like a join. I first of all find the department 20, I find the row IDs of the records in the department number 20, and then I go to the actual table and get those row IDs. And that's kind of a join on row ID. So an index is, yeah, it's a redundant copy of the data, as evidenced by the fact you can say drop index and create index, and it gets the data back again. It can recreate the contents of the index from the contents of the table. And it accelerates queries. If you say just, select count distinct department number, it can more easily do that from the index because the department numbers are sorted than going to the table. So yeah, it accelerates a bunch of queries that you wouldn't even think of as index queries. So the next thing is a covering index. So let's suppose we take that same index and rather than storing row IDs, we store the employee number. So now we've got the same number of columns in the index as we have the table. In other words, this really is it's a copy of the table just in a different sort order. Now we don't need the row IDs anymore, which is good news because analytic databases don't handle row ID lookups. A row ID lookup is a random access to something which is 3 server rooms over, and it's a very expensive round trip. So analytic databases don't even bother with row IDs. So now we've basically just got 2 copies of the table, and when someone sends a query, we can just choose A or B, whichever one is more suitable for that particular query. And in fact, you could say which table is actually, the primary copy. You could say, well, the one sorted on department number is the primary copy, and the other one is a redundant copy. There's the same information content in both. Now, if I'm writing a query optimizer, how do I tell the optimizer this thing exists? That's kind of what motivated me to add this kind of stuff into Calcite. I didn't want to write covering index support into Calcite. I wanted to build some kind of theory that allows me to model these redundant copies of data. And that thing is something I call a materialized query. I hope you're beginning to see a pattern here. Let's give another example which is a bit further away. Oh, I preempted myself. So here's a materialized view with literally the materialized view DDL. And in Oracle or other systems that support these, I'm saying, here's the table, here's a query. The contents of the table are always the same as the contents of the query. And the most important thing is, I don't have to reference that table, the emps by depth now. I don't have to reference that in the query. If I do a query which can be satisfied by this, if I write a query that can be satisfied by that relational expression, it will use the materialized view transparently without me needing to do anything. So this is exactly the same as that covering index on the previous slide. But the interesting thing is that SQL in the create materialized view can be something very complex. It can be joins, group bys, exists, unions, all kinds of things. Here's another case where materialized views help. Let's suppose, who's used a spatial or geospatial system? Okay, probably used PostGIS or something. PostGIS was a huge amount of effort to develop, adding geospatial support into an existing relational database. There's been some research done about how do I add spatial support to a data, and sorry, to backtrack. The reason why it's so difficult is spatial data is difficult to deal with using the same, usually with relational data. There's 2 ways of accessing the data. You either access it by range, so everything between, department numbers between 100 and 200, or you access it by hash code, so all department numbers that hash to 7. Spatial data, you can't use either of those techniques. You can't do a one-dimensional range scan, and you can't hash. So you have to add these dedicated spatial data structures, and that's what they did in PostGIS, and it was an awful lot of work. But there's a trick to add spatial support to databases without altering the underlying storage structures of the database, which I'm about to show you. And we're thinking about this query, so we've got a bunch of restaurants in 2-dimensional space, and we're interested in restaurants that are within, 2 squares of that yellow circle in the top right-hand corner. 1.5. Within 1.5, a distance of 1.5 from the coordinate 6, 7. So the trick is to convert this two-dimensional space, which is the latitude and longitude coordinates, into a one-dimensional space. But we still want to, the trick is to ensure that if 2 points are close to each other in two-dimensional space, then they are likely to be close to each other in this one-dimensional space. So a space-filling curve, the Hilbert curve is the most famous space-filling curve, but there are other space-filling curves. Every point in this two-dimensional space is reached once. This curve travels through every point exactly once. So everything has a coordinate. Every point on this space has a coordinate on the one-dimensional curve. And the locality thing is really important because I want to be able to do a range scan on this along this curve in order to be able to find all those restaurants in that particular area of the map. It's not always one range scan. Maybe in some cases you need 2 range scans or 3 range scans. But anyway, you're still accessing only a small proportion of the curve. And by the way, I think of it as the easiest way of thinking about this is that the coordinate on the curve is a value between 0 and 1. So rather than going from 1 to 4, think of it as going from 0 to 0.25 to 0.5 to 1. So how do we use this in a materialized view? What we do is we compute a column. If we've got our restaurants table with x and y, we compute a column h, which is the distance along this Hilbert curve. So here on the bottom right of the screen, there it is. And then when I see this, distance less than 1.5, I actually change the query to convert this into a range scan. And the database that's storing this, let's suppose this is HBase. HBase is, has tables which are sorted by a particular key. If that key is H, then I can very easily do a range scan on that key. And find all the restaurants in that region. There might be some false positives. There might be things that are on the curve but are slightly outside that 1.5 kilometer radius. But it works pretty well. And HBase is not a spatial database. We're just using this sorted table, which is the main data structure of HBase. So this is pretty cool. And so this materialized view is not a new data structure. This materialized view is simply a very small piece of knowledge that the optimizer has when the query is coming in that says, I can safely do this rewrite with this query in terms of x and y to use this h column. So I think this is a pretty neat trick. So I think I covered a lot of this. We tell the optimizer, we tell it about this h column. We tell it what expression is in this column. And then we put it, then the important part is we put it in a table which is physically ordered on H. And then we can get efficiently execute the query. Another area that's kind of close to my heart, another area of non-traditional SQL is streaming queries. Streaming queries are, real-time data is ever more important, and we need a declarative way of dealing with streaming queries and continuous ETL. And SQL is, SQL is not a perfect language for any application, but it turns out streaming SQL is a pretty effective way of defining continuous queries. And I've been doing a lot of work on this in Apache, working with projects like Flink and Samza and Beam. And one of the cool things about using SQL for streaming queries is in a streaming database, you are sometimes interested in continuous queries. In other words, tell me every time there's an order over 1,000 units. But I'm also interested in historic queries. How many orders larger than 1,000 units did I have between 1st of June and 31st of December? That's a historic query. That's a database query. That's not a streaming query at all. I'm interested in both kinds of queries, and I'm also interested in hybrid queries. So give me an order which is larger than the average size, an order which is larger than the average size of orders average size of orders for that particular product. That's combining streaming data that just arrived 2 milliseconds ago with data that's been building up over the last year. Because we're using SQL, we're actually able to combine streaming query and historical data. So SQL helps us solve the first part of the problem, which is how do we even express this question. It doesn't help us it doesn't help us actually implement it. So implementing this is hard. Now, how do we go ahead and implement this? If we're using, say, Kafka to represent our stream, the data that flowed a year ago is long gone from Kafka. So in order to implement this, we probably need something like the system kind of needs to know that data is flowing out of Kafka and, say, flowing into Parquet files that are managed by Hive or something. And so when it receives this hybrid query, it has to know that today's data or the last week of data is in Kafka and the last 10 years of data is in Hive and form this query. So that table of historic data is essentially a materialized view. It's the system knows where to find this bit of data and where to find that bit of data. So a materialized view is a way of telling the system where all the little bits of data are. And of course, I'm a query optimizer guy, so I don't tend to be very concerned with maintaining the data, maintaining the materialized views. That's someone else's job, but that is a big part of what the system does, is keeps that materialized view up to date as data arrives. So I've given you a list of 3 examples of things that can be difficult data problems that can be modeled by materialized views. That general idea of having a table and a relational algebra expression that says what's in that table is incredibly powerful. And I think it's a pattern that we will start seeing over and over and over again in the next 10 years of data management systems. So, how long do I have left? Okay. How do we design these materialized views? Simple answer is users can do it, but that's a very imperfect answer. So what the first answer is always humans tune these systems. The second answer will be we would like the systems to adapt, maybe in fairly minor ways to start with, but get smarter over time. So imagine we have this recommender, right? The input to this recommender ideally would be the DML, in other words, the definitions of the tables they've created, the queries that have been seen historically, and the statistics. In other words, this seems to be a primary key. This column seems to have 20 unique values, all of that kind of stuff. And this recommender would see all of this data, including queries that are arriving in real time, and say, hey, I'm going to start producing some materialized views, or I'm going to reorganize this table. I'm going to repartition this table on product ID because I'm seeing a lot of joins on this. And I mean, there are simple forms of adaptation that we don't even think of as adaptations, but simply a cache is a way of building an adaptive system, right? It's just, I'm going to keep this data around because they just read it 2 minutes ago. There's a really good chance they're going to use it in the next 30 minutes. That's what a cache is. So as systems get smarter, then perhaps we can start having more forms of adaptation built into our systems. This is kind of where I'm heading at, thinking I've been involved in BI systems, analytic databases for a long time. This is kind of my holy grail that I've been working towards for probably the last 10 years. In-memory materialized views. So this idea where the gray bar at the bottom is the data on disk, and the circle at the top is this user that's sending queries via Tableau or whatever tool they're using. And when they hit a piece of data, what it should do is pull that data into memory, such that as far as the tool is concerned, it's still a SQL data set that it can use, but it's a piece of data in memory. And over time, the system is going, oh, they are interested in analyzing data in Texas and Arizona from 2014. Okay, I'm going to start building some summaries for that data in memory so that they're, the queries over the next hour are going to get fast. I did this the wrong way in Mondrian. I kind of built these caching, but I built it in Java hash tables, which were great, but there's just no way you can join a Java hash table to a table in Oracle. So it was kind of right but wrong. And then these are the kind of research problems we have to solve. A human has to deal with these problems, but the system is going to have to deal with these problems in the future. So figure out which materializations to create, populate them, perhaps populate them incrementally, rewrite queries. A materialized view is kind of useless if you have to reference it in your query. So when a query comes in, you have to recognize that this materialized view could be used to answer that query. And then over time, create new materializations to adapt to the query load. And then lastly, it needs to be expressive. So if you're dealing, we want to deal with an extended SQL that can deal with streaming, that can deal with nested collections, that can deal with like machine learning, complex event processing kind of structures, not just select from where. In Calcite we introduced this data structure called a lattice, which is it's kind of a space of possible materializations. So we were focusing initially on the problem of summary tables. If you're dealing with a BI application, then an awful lot of the queries are select from, where, join, group by. In other words, they join several tables together, a fact table and dimension tables, and then aggregate on some combination of attributes. And a summary table is a very useful form of materialization to create because it saves you from reading a lot of data and it doesn't occupy a lot of space. A summary table is often, thousands of times smaller than the original data set. So a lattice is kind of telling the system about the star schema, what are the dimensions and what are the measures, what are the join paths here. And so once you've created a lattice, the system will start watching for queries that are coming in and start thinking about possible summary tables it could create. The problem is there's a lot of possible summary tables. So if you even have 10 attributes, 10 columns, for example, 10 dimension columns, then there's 2 to the 10 possible aggregate tables you could create. So as you can imagine, and on this diagram, I've kind of diagrammed out some of each of the ellipses as a possible summary table. The one at the top is the grand total. It only has one row. You've got a summary table summing by zip code, which has 43,000 records in it. You've got one by month, which has 12 records. The one by year and month has 60 records because we've got 5 years worth of data, and so forth. And then at the bottom is the raw data, which is, say, 1 million rows. So as you can see, as you have more items in your group by clause, the size of the summary table gets larger. As you have fewer items in your group by clause, the summary table gets smaller, but it can answer fewer queries. So so here's a typical set of summary tables that we would choose. The orange ones are the ones we've decided to materialize, and if you look at virtually every query, will hit one of these. If you come down from the top of the graph, virtually every query will hit one of these, and therefore we'll be able to use that. So if, for example, I have a query on zip code, I will hit the summary table, which is on zip code, state, and gender, which has twice as many records approximately as the zip code, but that's fine. I can easily roll it up. So there, I'm going to skip, in the interest of time, I'm going to skip over the algorithm to generate these. In fact, I'm running so short of time, I'm probably going to skip over a lot. Oops. There we go. The algorithm to generate these summary tables actually is a voracious user of statistics. So one of the features we added into Calcite was data profiling. An algorithm which can basically do select count distinct x, select count distinct y, select count distinct x comma y for every combination of columns in your database, and just figure out which are your primary keys, which product color is functionally dependent on product AD, so it can discover these functional relationships and therefore figure out before it goes and builds them what the size of these summary tables is going to be. And I'm going to skip over this, but long story short, the algorithm makes extensive use of hyperlog-log as a way of doing approximate counts to kind of grok the contents of your database. And here's a kind of the algorithm runs iteratively. It starts off by just looking at single columns. Select count distinct x, select count distinct y, and then when it finds columns that have unexpectedly high cardinality, it then tries combining them together. And it runs adaptively until it basically is no longer surprised. A surprising combination is when state and zip code have fewer combinations together than they would have individually, which basically tells you they are, in statistical terms, they're not independent variables. So based on this, in a small number of iterations, the algorithm can basically come up with a pretty good estimate of all of the functional dependencies in a star schema. So I am going to, and there's another feature in Calcite which basically you don't have to specify any business model at all, but can just observe the queries coming in and noticing that you often join the sales table to the customer table, and in another query you often join the sales table to the product table and the product class table, and therefore infers what your star schemas are based on the incoming query load. So to summarize, materialized views are, the one thing I want you to take away is materialized views are important, and we're going to see a lot of them. And they enable not just high-performance systems, but they enable systems to learn from the query history, the query activity on the system. And relational algebra relational algebra kicks ass. So.
Thank you so much for your talk. It's just so great to place a face with a name. I remember installing Mondrian for the first time back in like 2005.
Yay, it was you.
It was me. And I was like, oh my God, this guy's crazy. He's giving away SQL Server analysis services for free.
I know. Us open source people are insane. But still, we find people to employ us, so.
My question was, in terms of, I haven't really looked under the covers at Calcite. Does it give any guidance in terms of things like, oh, I'm pulling things into memory cache, therefore if I'm on a cluster of query machines that are providing the compute, that I should shard the cache? Like, is there that kind of, okay.
Yeah. Indirectly, yes. So Calcite as a query optimizer has statistics. So you should, looking at a particular query, you can look at, you can look at the statistics of that query and figure out what its memory utilization is. And if you're using more memory than your cluster has, then at least it can tell you something is wrong. Calcite doesn't provide that directly, but indirectly it's giving you the tools to self-tune the system. I think this is kind of the downside of open source, is we tend to produce tools, but we don't produce full product. So what I'm talking about here is some of the tools in the toolbox that can be used. That would be an excellent product to build, and Calcite gives you all of the raw materials to do it. I mean, a set of statistics, that can look at a piece of relational algebra and tell you how much memory it will use is, it's taken a lot of effort to build that. So you'd be building on some, very good foundations.
Question here. So I'm curious, what, if anything, from your talk you plan or hope to incorporate within Looker? My understanding is Looker sort of sits on top of the data warehouse, is agnostic to a lot of like the low-level planner issues that you talk about.
Yeah. Let's say some of the things. I mean, one of the things I liked about Looker is it leans, in common with Mondrian actually, it leans very heavily on the data warehouse. It doesn't try and doesn't try and make itself into a data processing engine. So it generates some very complex queries and sends them to BigQuery and Redshift. But I think there are some areas where we are perhaps sending the same query or very repetitive stuff to the database over and over again. So we maybe can be a bit smarter about what we send. But I have no plans to radically change the way Looker works. I think just a little bit of intelligence in how we generate queries could improve things. Yeah, we'll see. My brother kind of noticed that I seem to kind of zigzag in my career. I will work for a BI company, then work for a database company, and then work for a BI company. So I'm on the BI company now. So the work I'd done on Mondrian motivated what I did in Calcite because I knew the databases were not providing what I needed to build a fast BI tool. Now I'm on the BI tool phase, and so we can maybe leverage some of the stuff in Calcite to be more intelligent about what queries we send to the database.